時半ぐらいに。登れば登るほど頭が痛い。体力ですね。あれが小持山です。っていうのは全部植物の違いなんじゃないかな。
Many of these languages have very complex dependency systems, and it could be a barrier to entry, especially if you're building or distributing software. So we're going to go through this and think about this from the very beginning of how you would think about containers helping you, okay? Now, this is a technical conference, so this is my last slide, if that's okay. Let me know, I can find lots of cat pictures on the internet. So we're going to be in this mode for a while, okay? So when I first started running programming, I was about 24 years old, and I had that book, and I wrote my first Hello World program, kind of like this one. And Python is like magic. You write a few lines, and you really believe you're a real developer. I started applying for jobs immediately after this was done. Senior developer, Python, 5 minutes of experience. And you look at this code and you're like, wow, this is pretty awesome. So I'm going to run it. You always automatically should know what this does. So we'll say Python, and then we'll say our app if you want. Okay, this is sweet. And then you go to your browser, and this is where your life changes for the first time. If you're new, when you see this is when you run around your house, and your spouse is like, what are you doing? That is not impressive. Like, it's a world. I can do that on a piece of paper. But it's important. Okay, now, I got Brave. My first Unix machine, FreeBSD. Right? BSD people are serious. They have like tattoos of the mascot. I'm like, that's not ever coming off, right? So we got this whole world thing going. So I was like, you know what I'm going to do? I'm going to run it on my server. It should be easy. I got this one file, this app py. So you copy it to the server. It's tiny. And then you go to type Python, and nothing's there. And then you become a sysadmin. In FreeBSD, you do not install Python the easy way. You have to heat your whole house from the server. You compile from scratch. This is what you do. So after about 6 months, I got Python on my machine, and the app didn't run. And then I needed pip. 2 years later, my app was running. It wasn't that bad. But this is what we're asking people to do when we write code. We're asking them to go and figure out what version of Python they have, what version of the dependencies they have. God forbid if you're using some C extension. And trying to use that on a Chromebook is very funny seeing that at the airport. Like, your computer's going to run out of battery in about 30 seconds. So we have all these dependencies, and packaging has come a long way in Python, right? So we have this ability now to say, hey, here's what my app requires. I can just do pip install. And I just did a little tweak. I'm going to show you guys what it looked like. So I'm on my Mac. I'm writing this test app for the demo. And I do sudo pip install. You guys are already like, what the hell are you doing? So I'm like, yeah, what could go wrong? I have Python pre-built on my machine. They're like, dude, the first rule of Python is you don't use system Python. I'm like, hold my keyboard, enter. You type in your password, right? And it's like, your InfoSec team is like, what the hell are you doing? Nothing works anymore, but I have Flask and everything I need on my machine. So we're winning. Like, I had to do this. So we have our app now. And we started to ask ourselves that there has to be a better way of doing this. So when I used to contribute to Python, I told you we had disutils, and there used to be a war, set up tools, disutils, and then we made peace. And the whole goal was not to reinvent the wheel. Let's improve what we have. So last night I was like, what is the state of the art in Python? And it turns out we literally reinvented the wheel. I thought this was a joke. I was like, no. It's not actually called wheels. They're like, no, man, this is what you do. And I was like, okay, wheels it is. So the truth is, packaging is a pain point for all languages. It's a pain point for all software. Things that work well are like your mobile device. You go to an app store, you bring the whole package down. And the reason why we can have a billion devices is because we do not ask users to go and install other software to use the software that they're interested in. It's simple as that. But we do the opposite when it comes to servers. We're making everyone's life difficult. Anyone ever heard of DevOps? Anyone know what DevOps is? I took a stab at it. DevOps is group therapy for systems. And we needed it largely because of packaging. It's not just Python. All those packages need to be maintained. They need to be updated. You write a Python app and say, hey, install this, and all the systems just sleep. So how do we make this better? And this is where I think containers become interesting. How many people think static linking is a good idea? How many people like containers? It's amazing to me that so few people think static linking is a good idea, but they like containers. This is static linking on steroids. It's a big tarball with everything. A full operating system is in there. You're linking everything. I saw one container that had like a Chrome browser in it. I'm like, what are you doing? So what we want to do is, how can we leverage these containers in a very smart way? So just so everyone's on the same page, a container, there's two parts to this. There's a packaging format. The goal is we package all our dependencies into a tarball. It is actually a tarball. And it's a tarball with a specific format, so we know how to download it, extract it, and be very efficient with layers. So what we're going to do is build one of these things. Now, I cache for this because these days, no matter what app you build, for some reason it downloads like 2/3 of the internet in order to work. But I'll show you what one of these looks like. So we have our application. So what we're going to do is start with this Docker file. So the Docker file here is, you'll see the first line there. It says from Ubuntu. Yes, that is an entire operating system to put our 2K application into. Now there's a reason for this. How many people here would say they honestly know all their software dependencies? Exactly. So when you don't know, you just bring in everything until it works. And then we get DevOps. So the next thing I do here is, there's a couple things happening though. We take all the tribal knowledge from wikis and runbooks, and we put them in a Docker file. Now this is not the best we can do, but it is a good stepping stone for the majority of the people building software. And we can do clever things like cache some of the layers. So even though that first layer is pretty big, it's actually about 70 so megs. We can cache that on the servers, so we don't have to copy it once for apps. Okay? So the next thing we're going to do here is going to do apt-get install Python 3. Everyone's using Python 3 by now. Please tell me it happened. All right, just clap in case you just pretend. And then we copy our requirements.txt into place. Now the goal of this whole thing is that now everyone has a very sane and clean build environment they can build their application. You can either give people the raw Docker file and they can build it themselves, or you can build it and store the artifact. Right? So if you've ever built any package of any kind, the goal here is to build an artifact and we'll store it somewhere. Now once we have the artifact, we can give someone the image name and they can run it. So we'll just build this here so we can see what we're talking about. Now, my Python is rusty. So if you see any bad code today, please give me a pass. Do not put it on Twitter. I promise to follow Pepe later. Okay, so we have this entry point. So this is basically going to do the same thing I was doing on my command line. And we're just going to set that in an entry point. All right? So we're going to make a target. This is a very fancy way of doing it. So we'll just do this Docker build command. So here what I'm doing is saying, hey, I want to build this image. I want to run that command, but what I want to do is have all of the requirements be pulled down and run inside of a mature root environment so that I have a clean build that's reproducible. So we'll run this now. Okay? So what we think is here is that I'm having a bit of caching. So I didn't change any of the lines at the top. Now you can run into issues with some of this caching, but the nice thing is when you're building and running applications, you want to iterate fast. You do not need to run the whole entire apt-get command or the pip command again. Those live as separate layers. So once you have that, we can just copy in our application and then we can run it. How many people think it's really easy to run multiple copies of an app on your machine? Not a lot of hands. How many people are using virtual env to solve this problem? Okay, so if you're familiar with virtual env to give us multiple Python environments, you can look at this runtime. So this is the other part of the equation. Once we have this tarball, we can run it under a runtime. So let's do this really quick. So we'll say Docker run. All right, so what we're going to do here is we're just going to run our app to make it a little bit easier. So we're just running on 5,000 to 5,000. So we're just doing a bit of port mapping so I can get to it. We're going to run this hello world app. It's going to run in the background. So at this point, I should be able to hit it in my browser. And there it is. Now I can run as many copies of this as I want to maybe map to different ports. But this only solves the laptop problem. We have the same package. It's easy to distribute. It's easy to run as many copies as I want. But what happens if I have 5 or 20 servers that I need to push this to? How many people are familiar with scheduling? Every hand should be up. Every device that you have has probably more than one CPU effective scheduler there. What most people are doing these days in lieu of a scheduler, we call it like the meat cloud. Okay? This is where you say, hey, run this application, and a human decides where it runs. And sometimes we track in a very fancy database, aka spreadsheet. And the problem with this is, if one of the machines dies, they have this thing called on-call. Okay? Machine goes down, you get a call, and you get to put the app back on the machine. So what we want to do is like solve this problem in a way that goes a little bit further than our laptop. So we have a tool called Kubernetes. Now, there's other tools that do very similar things, but we're going to work with this for now. So I have about 5 nodes in my cluster. Now the goal with this is that I do not want to statically assign my apps to machines. They're designed to go away. I want to treat each machine as one collective or like a multi-CPU system and treat the whole cluster like a single machine. So we need a new API, we need some abstractions. So once I have this abstraction, we can package our container and what we call a deployment. So let's look at this really quick. So we have this deployment object. So here is the container we built, and we have it hosted somewhere. So anyone that wants to run this app can pull this particular container image. Now some of you are like, well, how does the system know where to put this? Since a lot of people didn't raise their hands about what a scheduler is, I'm going to explain it. Now the fastest way I've done this without diving too deep into computer science and hijacking my whole talk, we play a game of Tetris. So how many people here say they have fully automated deployments? Okay, now this is a worthy goal to get to. You click a button, and your app installs to specific machines. I'll show you what that looks like. You do that in Tetris, I'll show you. It looks like it's amazing, by the way, if you can get to this point. So the goal is we want one-click deployments of all of our apps. Now you need to know a whole bunch of information ahead of time in order for this to work. You need to know all error scenarios. You need to know if a machine is in maintenance or not. And you need to make sure there's no network issues because you need to be able to route around them all in Bash. Python if you're lucky. So what we're going to do is, this is one-click deployment. This is the DevOps holy grail I'm about to show you. Be ready. You ready? One-click deployment. Bam. One click. And then you leave. It's fully automated, by the way. But the problem here is your memory and CPU is just on the floor. And you're losing. Now we're going to cloud provider. This is pretty good, actually. Let's spin up more VMs. So what does the scheduler do? So here's the difference. The scheduler has to actually examine every workload as it comes in. Now, this is the x86 architecture. You're not doing anything that fancy. But things are slightly different, so they have different shapes and sizes. The goal is we look at these workloads as they come in, and then we make a decision. So what Kubernetes does out of the box is what we call bin packing. So let's look at what that looks like. So here, we see a workload, and the goal is just to place it by examining it. Now we look at these workloads as they come in, and what we're doing now is just scheduling in a way that we try to utilize all of our resources. So this is memory and CPU. I'm looking at all these workloads coming in. Now half of you are like, wow, this dude is really good at Tetris. If you can totally talk and play Tetris at the same time. Okay, but this is still bin packing that's happening here. Now you ask, why is the scheduler doing this? Well, when we examine all the pieces here, what we want to do is make sure that we allocate things in a way that, imagine a machine learning job comes that needs that CPU, and you've been reserving that special machine because it costs a lot more to run things on it, and when the right workload shows up, you can place it there. And then when it's done, you get back all the CPU and memory. You got a Tetris on Twitter. So that's kind of the difference between just automation and this idea of orchestration. We want to have this online examination of every workload so we can actually use our machines effectively. And the goal here is that we want to be able to reuse CPU and memory the best way we can. So it's part orchestration. So how do we do that for our own applications? So for our own apps, we have to make this deployment descriptor. Now, it's a big YAML file. It's declarative. But what you'll see here is that we have our app name. It's called Hello World. And then we're saying, Kubernetes, when you run this thing, I want you to go grab this particular image. And when you grab that image, I want you to extract it and run whatever the entry point was. Python, app py. And then I want you to also shape this workload. Now, the thing you got to think about, in order for us to schedule these things properly, we need to know the shape of the piece. This is why we have our memory and our CPU requests, so we know where it fits in the cluster. Okay? So once we have this, we can actually give it to Kubernetes. So kubectl, get pods. So what we'll do is we'll create this deployment object. Now, can anyone tell me what machine that it landed on? There's a breakout like, number 4. Like, no. The scheduler's going to figure out at runtime. The only thing we are asking is that we declare that we want one of these things running. So I say kubectl, get pods. We'll see that it's running somewhere. Now, the nice thing about this, let's look at what machine it's on. So it's on NF6P. And it has its own IP address, .90. But what happens if we were to destroy it? Alright, we're going to destroy the workload. Now, depending on where you work, you're either fired or you're going to get a call. So we delete the workload, and this is what we expect. We expect it to be replaced quickly, and it has a new IP. And the nice thing about a system like this is, when we replace the workload, we keep track of it. We know its IP address, so we can hook it up to the load balancer automatically. Now, if you've been doing this kind of work, this is just from decades of people doing these patterns, and now we've just baked into the infrastructure itself. It's kind of like the Python standard library. It's massive because there's no reason for people to rewrite these things over and over again. So these are things of pretty standard issue. If I look here, get SVC, we'll see that we have a load balancer that's routing traffic to all of those. So no matter what I do, I have a stable endpoint where I can hit my application, and there we go. It's up and running. Then it gets really complex. You're just like, you can't run production Python by just using Flask. And you want to know why? One request at a time. I do that at the my shell hanging. One request at a time. So what do we do? So in the Python world, it's common to pair with maybe some Whiskey server or Nginx. So what does that look like in Kubernetes? I'm about to show you a lot more on the screen, so be prepared. So in the container world, one would say you build an even bigger Docker file. And you install Nginx in there, you put your Whiskey in there, and then you take a script to launch all of that in the background. Great. You just invented an init system. There's no reason to do that. What's a better approach? Well, we don't want to pack Nginx inside of our apps container. We want those to be separate. So what does that look like to be separate? So here's another deployment object. And this time, we'll do things, and this is like I'm going to walk us through it really quick so we all can understand. This has multiple containers in them that we can stack. Think of it like a virtual machine. They're just going to run as processes that are co-located together to form the logical app. So at the top we have Nginx. We're using Nginx graceful shutdown. And then what we also are telling Nginx to do, you'll notice here this particular line. Here, we're going to share this particular path. And what's going to be there is going to be our Whiskey Unix socket that is exported from our app, so we can actually send traffic to it in the way proposed by their particular docs. So here, we are sharing a file system. One container is going to write its socket there, and another container is going to pick it up and send traffic to it. But the nice thing about this is, everyone knows how your infrastructure is composed. Nginx stands alone, and the app stands alone. So at this point, we can actually have Kubernetes manage this for us as well. kubectl, create, deployments. Alright, so once this is online, get pods. Great. 202 ready, so we can actually compose these things. If you need any helpers, you can run your helper scripts as well. Now, once you have infrastructure like this, you start to think about, why do I need to use conventional ways of interacting with it? I've been using command line tools this whole time. So in the Python world, one thing that has been amazing over time in Python has been used as a facade for more complex systems like TensorFlow, most big data stacks. Python makes it super easy to interact with things. So if I were building new tools, how would I interact with this? Now, I think if more Python people showed up to the Kubernetes community, they would also look to simplify things. So I found a really good Python library. So I wrote a new interface to Python, and this is the first time I'm going to show it to anybody. Okay? So if it doesn't work, remember, I wrote this yesterday. So bear with me, okay? So what we're going to do is clean up here a little bit. Get pods, kubectl, we're just going to delete these deployments. So it's really easy to spin these things up and down. Let's clear them out. And keep in mind the frame of reference I'm coming from. I've been watching Star Trek The Next Generation for some reason on Netflix, so I really believe I'm living in the future right now. So when I went to go build this thing, I wanted something that felt like that. Okay? So let's just do a watch on here. I'll show you my new tool. As you can tell, I'm a bit shy here. So please don't laugh at me if this doesn't work. Alright, so let's just terminate. Let's clean things up. Man, do you know what it's doing? It's trying to gracefully shut down. Alright, we're down. Okay, so we're going to try this thing. So, an app I'm using was shipped on Wednesday. So this is just devil, not smart. Encompass Wi-Fi. Okay, Google. Talk to Kubernetes. Hold on. We may have to go to airplane mode because I might need the bandwidth, okay? Okay, Google. You better work as people are watching. I spent all night on this too, so talk to Kubernetes. No way. Hold on. We're not going to abandon ship on this. I will be up here for 6 hours if I have to. You just ignore the whole speaker timer. Okay, Google. Talk to Kubernetes. What? It's sitting here like, I got it. Let's do this. Maybe I need the test button. Maybe need that. But you guys like when the live demo doesn't go well. You're like, it's going to fail, I know it. My apologies. I don't understand. Talk to Kubernetes.
This is the top result.
Talk to Kubernetes.
Here's the top search result.
It's trolling me. Okay, Google. Talk to Kubernetes.
Sure, here is the test version of Kubernetes cluster.
Hello, Kelsey.
Hi.
Looks like you have a large crowd this time. I hope the demo gods are on your side.
What's my cluster status?
The PyCon cluster is running with 10 CPUs and 37.5 gigs of RAM.
Run the Hello World application.
What image tag would you deploy?
1.0.
Deploying Hello World 1.0 into the PyCon cluster.
So we got that running. Scale the Hello World deployment.
How many replicas would you like?
500 divided by like 10 minus 40 minus 5. 5?
Scaling the Hello World deployment to 5.
Now here's the thing. It's easy to do deployments. How many people have ever done zero downtime deployments? You liars. You still got on call. No, it's a tough thing to do. So the holy grail is to do these zero downtime deployments. So we have 1.0 running right now inside of our cluster, and the goal is we want to upgrade this. So this is the nice thing about this fully API-driven world, from the networking to the storage to the app itself, also around auto-scaling. So what we want to do here is see if we could update this in place without dropping any of the packets here. Okay? Update the Hello World deployment.
What version of the application would you like to deploy?
2.0.
Updating the Hello World deployment to version 2.0.
Thank you.
Okay, I gotta admit, that was pretty dope.
And with that, I'd like to end the presentation. Thank you so much.
I gotta admit, that was pretty dope.
Welcome to my talk, A Brief History of Time, by Raymond Ettinger. In the beginning, the dinosaurs roamed the earth. They died and became extinct because of their inadequate capabilities. In the void that they left behind, the mammals arose, and intelligent life came to this planet, and we invented Python dictionaries. Any questions? Would you like a few more details? All right, so my name is Raymond Ettinger. The theme of my talk is lots of smart people over time thought about the dictionary problem very, very deeply, came up with some ideas, presented their ideas, the world accepted them, and thought we had good dictionaries. Then someone else came along, thought about it very deeply, and had another innovation, and another innovation. And I think what we have today is a confluence of about a dozen great ideas that span the course of about 50 years. And so I'd like to take you from the dinosaur era up to the present, and then slightly into the future. There are those of you who know nothing about hash tables. You will know everything about hash tables shortly. There are those of you who learned about hash tables in school. Now you'll learn how they're done in real industrial strength production code. There are those of you who already knew that, but don't know what the latest innovations are in Python. We have propelled the future quite a bit forward in the last few years, and I'd like to take you on this journey to where I think it's a somewhat magnificent, I call it an ending point, but evolution never ceases. Shall we begin? All right. So one little thing about me, what is my mission in life? It is to train thousands of Python programmers. I personally trained about 5,000 programmers. My company, Mutable Minds, Inc., I have a team of trainers, and we have trained about 13,000 people cumulatively. So if you have an interest in such things, call me. And let's begin. All right. Our journey. The beginning and the end. Let's do the overview first, which is... Where is... Do not reprogram your keys just prior to a presentation. There you go. So the importance of Python is built around dictionaries. Globals are dictionaries. Locals were at one time actually dictionaries. Modules have dictionaries. Classes have dictionaries. Instances have dictionaries. They're central to the language, which means that they're used everywhere and they're pretty darn important. One example is we have instances. So we have a class and we have several instance variables. And I've chosen Guido, Sarah, Barry, Rachel, and Tim, all important people in my life. And I remember to show them. We've made 3 instances, a color, a set of cities, a set of fruits, so that we know Guido's favorite color is blue, his favorite city is Austin, and his favorite fruit is apple. I just made all of that up. And we can loop over the instances and print them out. Common place everyday Python code. What I'd like to do is look what's behind it and look what it looks like. So behind each of these 3 instances is a instance dictionary. Where is the make big button? That is my favorite button. There we go. Okay. So we've got 3 dictionaries, Guido blue, and then the next one Guido is Austin, and the next one Guido is apple. And so that's a consequence of how Python is designed. Instances have dictionaries behind them. So what we'd like to do is see how these dictionaries are implemented over various versions of Python. Jumping right to the end to see where we ended up after all the evolution. In Python 2.7, each one of these dictionaries took 280 bytes each. And the ordering of the dictionary was Sarah would go first and Guido would go last. And that is deterministic. It is repeatable in Python 2.7. And the keys are scrambled. We actually say arbitrary because they're not re-scrambled every time. In Python 3.5, some things had changed. By 3.5, the size of the dictionary had gotten down to 196 bytes, which is very nice compaction. And this time, the keys are actually randomized so that every time you rerun it, you get a different key order. So they were no longer deterministic. Then Python 3.6 came out. It's the size a little bit smaller, 112 bytes, which is pretty darn amazing. And the key order is now deterministic, and it's the order that you added the keys because, after all, in the beginning, there was Guido, and from Guido came everything that you see around you. Okay, so Guido goes first, always the ruler of the kingdom in the order of dictionaries. In the Python 3.5 universe, he was just another schmo. Once in a while, he'd get to be a benevolent dictator. Once in a while, the rest of us would get to tell him what to do. In Python 2.7, he was always on the bottom of the list, and Uncle Timmy took priority. But now, he always gets to be king. And so that's where we're going to end up at the end of our journey, is with smaller dictionaries that are ordered. By the way, how many of you like small and ordered dictionaries? This is a fine thing. It's one of your reasons to want to upgrade to Python 3.6 straight away. I'm not going to say that I was a Python 3 holdout because I've been working on making it better for about 8 years. That said, I believe Python 3.6.1 is the first of the Python 3 series that's actually better in many, many, many respects. It is very, very, very good. It is now time to really push hard on other people to go ahead and just switch over. When I step back to 2.7, which was a nearly perfect Python, it feels like a dinosaur to me. And you'll see part of the reason why coming up. So let's start back in time with the dinosaurs. Okay. So the dinosaurs were our parents and our grandparents who had this bright idea of using databases. And in a database, we had rows and columns. And the columns were each fields, the name, the color, the city, and the fruit. Now, our forefathers weren't entirely clueless. They came up with the bright idea of indexing into this database so that you could do quick lookups for berry. But clearly, our ancestors, our parents and grandparents, had no idea what they were doing back in the 1960s when they made databases like this, or I should actually say early 70s. This design was from E.F. Codd in 1970, who announced onto the world all at once relational database theory. So this is the state of the art in 1970. The dinosaurs who died and became extinct because their skills were inadequate in comparison to our awesome skills of today. Their parents were unequal to us. They would shiver to see our modern code. Just saying. This we all know is true. Programming has advanced dramatically over 50 years. Do you believe me? It's a trick question. Do you believe me? Do you believe me? It's a trick question. Ooh. Okay, so I've got a little setup here. I've got some keys, some values, 3 sets of values. I create a list of hashes, a list of entries, and combined entries that have the keys, hashes, and values. These will be the data structures that I use through the rest of the talk. So what is a database way of solving a problem? In Python, we would represent it as a list of tuples. The problem with this is we have to do a linear search, and so as it starts to scale, the performance is really bad. Interestingly, compared to modern dictionaries, once you get to a list of size 2, you are not as good as a dictionary. So we tend to think of scaling as like, if you've got 1 million entries, dictionaries would be better. But typically, it's about 2 or 3 when dictionaries start to win, which is pretty amazing. I know what you're thinking. Oh, that was a trick too. There must be a worse way than this. There is. Unto them was born a crazy group of people known as list programmers. And the saying was, a list programmer knows the value of everything and the price of nothing. So a list programmer would store what we're called association lists, the key value pairs. So in this case, we have a list of tuples. Each one of them needs to be searched independently, but you can see there's a linear search for each of these, and we have multiple lists, and there's redundancy inside, wasting space like crazy, like list programmers are wont to do. Just saying. Remember, the dinosaurs, our parents and grandparents, were crazy people and didn't know all of the things that we know today. That's a trick. All right. So, what was the first innovation after the dinosaurs died off? It was called separate training. The idea is, instead of doing a linear search of a big list, how about do smaller linear searches of smaller lists? So the idea is take that one big list we had before and divide it into 2. This is list number 1 and list number 2. Now if you search list number 1, you either get 1 probe to find Guido or 2 probes to find Tim. 1 for Sarah, 2 for Barry, and 3 for Rachel. This doubles the performance of the lookups as long as you know which bucket to look in. And you know which bucket to look in by hashing. If somebody asks you for a simple summary of what hashing is, it is reducing the size of the search space. So if I was doing a linear search of this room, I would have to go through 600 people. If I know which cluster you're in, cluster 1, cluster 2, or cluster 3,